right? You should be able to even to write down the equation. But what happens if I increase the energy? Now the motion is very... Okay. You say, well, I mean, the friction is stopping, but... But you see, you more or less, you are convinced that this is very unpredictable. Even if I try to launch the pendulum from the same position every time, it makes something different. So there is a parameter here, energy, that if it is very low, it is regular motion. If it is higher, it is chaotic motion, in some sense. You see. So what happens if I increase the energy? It should be more chaotic, right? Let's try. No, it's more regular. Well, again, because of friction, but I mean, you saw at the beginning it was going around. So that was very regular, right? It was just rotation, pure rotation. Okay, well, we know something. Let us try to do some simulations. Excuse me, because the program is very old. So I have to do this. I don't know. Maybe the older people here. It used to this. Everybody knows this. DOS. Do you remember the US? Not everybody.
Not everybody.
Well, it's like right. It's like dinosaurs.
Thank you very much.
Well, I mean, no, I know a lot about DOS. I worked at DOS. So, I mean, but you know, the thing is, I have a program that nobody has changed it. Do you remember deer? Tell me the deer.
Yeah.
Okay, this is the program. Okay. You see, well, there are several examples. I'm going to show you the triple pendulum. This is the normal pendulum, right? But I can change the parameters. I can change this parameter 8.7. You see it, right? Okay, so I have different views. So this is the sine of x versus t, the position, the angle versus time. You see, it's fairly regular, right? It seems very regular.
Yeah.
In whatever sense. And even this, I will tell you what this is. Okay, I'm going to change the parameter to see if I get something more interesting. Let us go to 0.5. Well, you see that there's something more interesting. Now it's not just an ellipse. It is like a more complicated ellipse. So let us see the views. Well, here you don't see much. But yeah, you see. It's like with my pendulum, right? Sometimes the oscillations are higher or slower, and it goes farther. So it's more chaotic, but it's still not very chaotic because, okay, I'm going to change A and see. Well, now it's more wide, right?
Sorry. What is a driven pendulum? What is
Good question. Well, once, no, it's a very pertinent. You see, I mean, now if I plot the sine of x versus t, it is, much more chaotic. But okay, that is a very good question. I mean, what is a driven pendulum? Maybe I should have. is what you wanted, right? Okay, everybody is familiar with Newton's equation here? Mass versus the second derivative of a coordinate is equal to a force. Everybody, are you with me? No? Not the students?
Most probably not.
But you know Newton?
Apple.
The apple?
Yeah.
Okay, so Newton find out that there was a fundamental equation in mechanics that was the mass of a body, like my mass, how much I weigh, times the acceleration if I run. So when I hit the wall and the wall stopped me, there is a force, and that force is my mass times my acceleration, which is the second derivative of the coordinate. You know what a second derivative is, right? I mean the students, no?
They are very young. Some of them may know it, but not all of
Okay,
them.
this is x double dot. Okay, so I put a damping term, which is proportional to the velocity, and sine is the force, and the driven pendulum is because you kick, you force the pendulum with a function. In this case is sine of omega t. So the parameter that was changing was a and omega. I was changing a. I was making the perturbation higher and higher. Okay, let us, if you don't like this example, let me show you another one, which is the three-body problem. Three-body problem is very easy. Two stars, like heavy masses, and a planet in the middle, going around. So the forces now is gravity, right? The thing that Newton find out through the apple. Okay, this is a very chaotic problem. Let me show it to you. Again, with the program, I have to redo the whole thing, but it is very interesting. Now we go to the three-body problem, and here we have two masses. This is a restricted three-body problem in the sense that we keep fixed the two stars. Let us imagine that they are very heavy, so heavy that they don't move, and it is the planet that really moves. Okay, this is chaotic. This is chaotic. This is no regularities at all. But what happens if I delete one of the stars? Here is the ratio of the masses of the two stars. So if I make this parameter 0, one of the masses will disappear. Okay, let us see what happens. We have this. What is that? People know? The student know? Do the student know?
What is this analysis?
You have the moon going around the earth, or the earth going around the sun. What is that? Who discovered that? Kepler, right? Kepler discovered that the motion was in ellipses, and the heavy mass, the star, was in the focus, in one of the focus of the ellipse. So you see that, and you know the program is running. So it's always running, as is happening in the heavens. I mean, we go around the sun every year, once every year. Okay, but I'm going to show you something interesting. Let us put back the masses back, 1 to 1. Okay, and now I'm going to put not just one single trajectory, but several at the time, with changing the parameter n. Okay, let us put 4 or You see, there are 8. They start very, very, very close together, but because the motion is chaotic, what they happen is they separate. At the beginning, the separation is small, but the separation grows and grows and grows and grows. It's like if 2 twin brothers were born essentially at the same time, the same place, from the same mother, from the same everything, but, you know, eventually they grow up and tiny differences make a whole difference at the end. And one may be a criminal and the other may be a saint or whatever, right? But you see, this is chaos. And this is chaos as one of the founder fathers of the theory shows, that was Henri Poincaré, one of the geniuses of the mathematics of all time. Okay, I don't need this program anymore. Let us go back to the presentation. So this is what I have essentially. I have 2 situations. Sometimes things are regular. It's like, you know, you are canoeing in a nice, smooth stream in a river, and you know everything is nice. Nice Sunday morning, or you can go more adventurous and, you know, do rafting. And rafting you can end up wet, because well, the first thing is regular, the second is chaotic, and you know the thing is that, you know, we can start working a definition of chaos. It's small causes produce big effect, or they are extreme dependence to the initial condition, as we have seen in the 3-body problem, right? Okay, let us see if I can. Okay, well, this is the same situation. Let us forget. But the person that, okay, Poincaré was the pioneer of chaos, but he did his work much ahead of time. I mean, nobody except himself and a few people like Einstein or really understood what he did. And at that time, there were not the power to develop his ideas because there were not computers. But in the 70s, this guy, Edward Lorenz, after the Second World War, he studied meteorology with the first computer, and he discovered the same effect, rediscovered the same effect. And he called it a butterfly effect. Because he gave a conference that said, can the flap of a butterfly in Brazil set up a tornado in Texas? Meaning, as I was saying before with the brother, with the twin brother, is that, you know, tiny differences grow and grow and grow. So tiny difference like the flap of a butterfly in Brazil. And that effect grows, propagates through the atmosphere, and end up triggering a tornado in Texas. Well, this is not a good example because, you know, northern hemisphere and southern hemisphere are not very well connected, etc., etc. But he always defended himself saying that there was an image, a very good image, because it became conversation. Even it went to movies. I don't know if you remember Jurassic Park. I'm gonna put it a little bit. If you want. Okay, you know, this is when they go to the island, you remember? And, you know, this guy, I always forget his name, because I always remember his character in that movie, The Fly, the Game of Fly. Okay, but that guy is a mathematician. He's a mathematician and goes visit the island, and he said this is going to be a catastrophe because of chaos theory, because tiny difference that you have not foreseen, you cannot prevent happening, is gonna destroy it. And the guy, the owner of the thematic part, say, no, I don't believe you, you are just a crazy mathematician, mathematics are not very important in real life. And here he explained to this couple what is chaos theory. And I mean, essentially, I didn't remember he take water and put a drop and say, well, tiny differences in your skin, imperfection, made that it goes to the right or it goes to the left. But it's the same idea that I have told you. So we can just that, you know, it has become so conversational that you know, it went to the movies, not just this one, other movies. Okay, what else do I have here? Okay, well you can quantify this. You can put this in a solid theory, as this guy did. This guy was Lyapunov, and say, okay, chaos, extreme dependent on initial condition. What is the most extreme function that you know in mathematics? Which is the one that grows the most? You know that? What growth? I mean, something which is linear growth, but something which is parabolic, which is the square, growth faster. Other polynomial grows even faster. But you know, the exponential is the one that grows the fastest. So you plug this, and you put a coefficient here, and this coefficient tells you if you have an exponential separation of behavior, or you have a mild separation of behavior, if you have chaos or you have regularity. Okay. So you think I should avoid this equation? You don't like equations? You will regret. You should change your behavior. Equation, I mean, we don't know why. All science, and by science, I mean not the hard science like physics, chemistry, but also other science like social sciences. No, we don't know why, but the best way to express it is mathematics, mathematical formula. Nobody knows why, but it is the most intelligent, efficient, powerful way to do it. So the more mathematical you learn, the better you will do in anything in this world. But you know, let us play a game. I'm going to show you something, a cousin of chaos. Let us play a game. You learn. Right. Okay. You take a sheet of paper and you draw 3 points. 1, 2, 3. And you label them. 1, 2, 3, 4, 5, 6. Now you pick up a random point inside the triangle, the green dot. You take some dice and you roll them, and you see that it's appear a 5, for example, a 6. Okay, so midway from the initial point and to the corner labeled 6, you draw a point with a pen, this one. And you do it again. You roll the dice and you find a 3 there. So midway from the newest point to the corner labeled 3, you draw a point. And you do it. And again, it happened to be 3. Well, no problem. Midway, you draw another point. And you do that million of times. What will you get?
Millions of points.
A what? A what? 1,000 points. Fine, good.
Okay.
This is. I will tell you a joke about mathematicians.
Yeah.
I don't want to take that. Okay, yeah. If you do it 1,000 times, you will get 1,000 points. But where will be those points?
Inside the triangle.
Inside the triangle. And if I do 1,000,000 points, what will you get? All. Sorry? Okay, you will fill out the triangle. Let us check it, just in case. But I think it's a sensible thing. Okay, you know Excel?
Better than DOS.
Yeah, better than those. Okay, so we have done this. But you know, I'm better in DOS than I am in Excel. Let me try to bring it to the. Okay, so I program in Excel that game, believe me. And let us play the game with a number of points. We say 1,000.
Okay. 100.
Sorry.
That's the maximum one you can.
Okay, well, this is what happened with
100.
with 100.
Yeah.
You see that your idea seems not to work. I mean, there's a big hole in the middle, and there are other holes. And the whole seems to be triangles. Let me
Wow.
try. Let me try to do with more points.
I see.
10,000.
Sierpinski.
Man. I would have said the same thing. I would have been
Sierpinski
wrong.
triangle.
Huh? Let us think about it. So, well, I could explain you why this happened, but I'm not going to do it. I'm just going to tell you what we got. Because what we got is a very interesting mathematical object. Okay. Well, this is the result. Okay, I could have construct that mathematically. Say, in the sense that I say, I have a triangle. I draw the midpoints of all of the three sides, and I delete the triangle in the middle. I get three triangles, smaller but similar to the previous one. I repeat it, and if I repeat it, I will get this result. Don't you think? Okay, what is this? Okay, I could do it in 3 dimensions. What I get is something called a fractal. Have you heard that word before?
Yeah.
Eh? Yesterday. Okay, well, and do you know that this guy, Benoit Mandelbrot, was the guy that brought fractal to the forefront of mathematics research in the 60s with this book, The Fractal Geometry of Nature. Okay, I was going to tell you this because if you know this, I can skip it. So the idea of Mandelbrot say, okay, in Euclidean geometry, we use geometrical objects of integer dimension. Dots have dimension 0, cube has dimension 1, surface is dimension 2, solid dimension 3, etc. But why not define object with fractional dimension? And this is what this is. This is an object that has a dimension which is not 1, is not 2, it's something in between. Do you know that? Or would you like to hear that? Do I do it or not? Yes?
You know?
Okay, let me try to convince you. Okay, so actually, I mean, it's not Mandelbrot that invented that. Fractal has invented by Cantor in the 19th century. Another big master of mathematics. So the idea is he defined something that was a fractal, and it's called a Cantor set. And this is the idea. I tell a segment of unit 1, this. And this is my initial step, k equals to 0. So I do another step in which I divide it in 3 equal segments, and I delete the central one. I get this. I got 2 segments of length 1/3. I do it a second time. I delete the middle third here, and I delete the middle third here. I do it 3 times, 4 times, infinite number of times. What do I get? Sometimes it's called Cantor dust. It's something that is intermediate between a dot and a segment, and a full segment. It's not a segment because I have deleted infinite segments. And it's not a dot, or it's not a collection of dots. It's something in between. And what is more important is self-similar. If I show you this at a certain scale, you don't know what the scale I'm showing. If I delete this, you don't know if this is missing or not, because it has a scale symmetry. Okay, the idea is, how do I calculate the dimension? The idea is the following. Well, calculate dimension is very complicated. It's a tough problem in mathematics which isn't solved. Hausdorff has done something, other people have defined other dimension. I'm going to do something simple for you, which is how my collection of points, how my set extend in space. So if I have dots, dimension is 0. I don't need, if I have a dot, I don't need a coordinate, just the dot. If I have points in a curve, it's dimension 1, because I need to say it is at the beginning, it is at the end, it is in the middle, it's here, it's there. I need a coordinate to define the position of my dot. If it is in a surface, I need 2 coordinates. So it's a dimension 2, surface is at dimension 2. Solid is at dimension 3 because I need 3 coordinates, etc. So the idea is this. I can say that it's like measure my set. It is like, what is the length of this segment? It's L. So how do I know it? It's because I have a meter, epsilon, which I put, and I count how many times my measure fit into the segment. Of course, I mean, everything is more involved. I need to do a limit, because if not, the last time, only by accident it will fit an integer number of times. But you know, you can solve that with limits. This is why you study limits in your courses in high school. Okay, the same thing you can do it with a surface, but now you do it with tiles. With tiles, you do the same thing you do with the floor at home. So you have n, it is the surface divided by the epsilon square. In general, if you have something of dimension d, this number scale as epsilon to the minus d, as you see here. So if you take logarithms, you know what logarithm is, right? No. Good. So logarithm of n is minus d logarithm of epsilon. So the minus, I put it logarithm of 1 over epsilon, and this part I divide it, I take it here, and I find out d. And this is the logarithm of n divided by the logarithm of 1 over epsilon. Okay, I have to do a limit. Remember? Okay, we have to do epsilon very, very small. But you know, we can do it. Okay, let's do it with the Cantor set. So in the first step, I have 1, I can measure it with a meter of measure 1. And if I take that meter and I put it, I will get n equals to 1. Here, I need something which is 1/3. And if I put it here, I will put it twice. Here, I will have 1 over 9, and I will put it 4 times. In general, in the kth stage, my meter will be 1 over 3 to the k, and I will put it 2 to the k times. If I plug these numbers into here, I get that the dimension of the Cantor set is 0.6309, etc. It's an irrational number, which is this. Okay? This is a fractal. You can define other fractal like the cock curve, which is essentially the same, but instead of deleting the central half, you replace the central half with 2. So you will get something bigger than 1. Okay, you do the same thing and you get 1.09. And the funny thing, the interesting thing is that fractals are everywhere. This is what Mandelbrot told us. This is, you know, you take a cauliflower, and if I take a little piece of cauliflower and I show it to you, it looks like a big thing. And it happens in trees are like that. There's a big trunk and branches and small branches and small branches, because this is a very efficient way to grow and deal with the nutrients. And this will happen in our body. If I will have to have a heart that pumps blood to every cell in my body, the first time it beats, it will explode because the pressure will be too high. But it's very more efficient. There are big arteries and veins that leave the heart, which divided in other and other and other and other. And at the end, they are very tiny capillaries. Same thing happen with lungs. Lungs, you need a big surface to exchange oxygen, especially when you run or when you do exercise or whatever. But I mean, how can you put a big surface into your chest? For example, a calculation says that the surface of our lung, of an adult lung, it is the same surface of a tennis court. Imagine that you put a paper covering, or whatever, covering a tennis court, and you wrap it together and try to put it into your chest. No way. But this was very efficient. This is what nature has used it. Oh, I'm going to skip this, I guess. Oh, but not this. You can do experiment with fractal. You can play with my formula. For example, you take one piece of a paper. Let us say this one. And you make a ball. You rub it and make a ball. Okay, you have the big ball here. Now you have a second piece of a paper. You divide it in half. Same thing I was doing like with the
Cantor set.
with a Cantor set, and you wrap it and you make a ball. And you put it. With the other part, you divide it in two and do it. You have something, well, you do it better than I'm doing it, right? You do it again, and again, and again, until it's too tiny, right?
To infinity.
To infinity, right, essentially. You stop, right? But you can do something like this. And then the theory is, if the density is uniform, the density will be the mass divided by the volume. The volume approximately is a sphere. And the volume of a sphere is this. It's pi, the diameter to the third power, divided by 6. So you can extract m, and I will give you this formula. If you take the logarithm, it will tell you that the logarithm of m scale with the logarithm of the diameter as 3. But the thing is that this, no way, can be uniform, because the way I have done it. It will be more like a fractal. So if you do it, you do these balls, you take a ruler and you make the diameter, and you make this calculation, this simple calculation. You don't need the mass, because, you know, essentially it's half, 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 half. So you choose the units, so that the first mass is 1. And you get this. The first mass is 1, the logarithm is 0, the 1 is 1/2, the logarithm is this, the logarithm is that, and you just have to measure in millimeters the diameter. You may this plot, the logarithm of m versus the logarithm of d. It should give you a straight line with a slope smaller than 3. Do it at home. I have not time to do it here. Another game. Where do I have this game? Here. Oh, by the way, I forgot to show you this. These are chaotic toys. They have magnets, and you see that the motion is chaotic at some point.
Yeah.
You see?
Yeah.
Or this one. I forgot to show them to you. This is another double pendulum like this one. Well, it really doesn't matter. But you will see that the motion is irregular. But I have this, which is a magnetic pendulum. Well, at the end you can see this thing. Okay, you see, I have, well, I'm sorry you don't see them very well, but you know, later you can. Okay, this is a pendulum, right? But it has a magnet at the bottom. And I have other magnets in my hand. So I can put them. And obviously, well, that magnet repels well, I can make it that attract. I can put another one. And then if I make it swing, you know, the two magnets will be fighting to hold it.
To get it.
Or I can do it with 3. And it will be more complicated. Or I can do it with 4 or whatever. Right? And you know, the trajectories are pretty chaotic. I will show you in a minute. You see? What did I do with the... Okay, well, I'm not gonna bother you with the equation, but they can be done. But this is the thing. So you have you have trajectories that eventually stop in one of the magnets. And then I'm going to show you this video. How much time do we have? Agatha, what time should I finish?
What time? I don't know.
It is
What time is it?
13.
it is 5 to past 12.
We can still have some time until 1 o'clock, perhaps.
Until 1. Till 1 o'clock.
To 1?
Yes.
Okay, let me do it 20 more minutes or so. So let me show you the video because it's very interesting.
An iron ring hangs on a thread, exposed to the force of gravity and the attraction of three magnets. If this pendulum is brought to any starting position and then released, it will ultimately come to a stop over one of the magnets.
Well, this is what I show you. And the funny thing is that now we are making a plot. I'm going to make a plot, putting every pixel in a screen the color of the magnet that stopped the pendulum. And let us see what happened. You will see that it is a fractal. It's something terribly complicated.
Any ball that is
Let us
released in
try
its
to speed
immediate
it up.
neighborhood, but each will also attract some balls whose starting position is farther away. Not good.
Well, these are trajectories. You see, okay, and this is how. So if the yellow magnet is stopping, I will do this pixel yellow. If the second trajectory starting at that pixel is stopped by the red, I will paint it red. So I will make a first sweep of all the pixel, and then I will increase the sensitivity, the accuracy. I will make it finer, 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 and let us see what happens. And we will have a surprise as we have with the triangle of the first game. This is what we get at the end. This is incredible. So if we start close to the blue magnet, we stop in the blue magnet. But if we go farther away, we can land essentially in any of the three magnets. It's unbelievable. And unbelievably complicated. If I take any small piece of this and I blow it up, it is full of color. It's full of color at every scale. It's like the Cantor set. It's a fractal, essentially. You see?
Well, red
So, for example, these are all
happens very quickly.
is an all point that goes to the yellow magnet.
Thus proving that the idea of an
See, so this is, I don't know what you think about it, but I think it's fascinating because it's something so simple which shows such a rich mathematical behavior, such big complexity, which is amazing. So, for example, this is all point that goes to this magnet, and that is stopped by this magnet. And you know, obviously, all these in the neighborhood are stopped by that magnet. But you know, there are other things that are launched. Okay, and if you want to play with this, you say, okay, I cannot play with that because the equations were too complicated. Well, there is something called Newton's method to find the zeros of a function. Probably you have not studied yet, but you will study. It's something very simple, and you can make it with that. And essentially, it's the idea. Imagine I want to solve this equation. C squared minus 1 equals to 0. What is the solution? Plus and minus 1. So it means that, okay, but you know, I can use the Newton method and start in any point in the complex plane. So if I start, this is minus 1 and this is 1. So if I start anywhere here, I will land here. If I start in any point here, I will land here. You say, no big deal. This is expected. Fine, but this is because there is only two magnets. There is only two roots. But if I do it in three, with the roots are here, here, and here, then every point, every point that I started here will land into the root here. And the same with the yellow, and the same with the blue. But in the frontier, there is a complete mixture of the three colors, right? Okay, and I was going to show you two more examples. Because chaos is ubiquitous. You can find it in every branch of science. Because the only thing that chaos needs to appear is that you have nonlinear coupled differential equation. And this is ubiquitous. Everything in science is expressed as a differential equation. Everything. So, for example, this guy, Leon Chua, that is a professor in Berkeley, constructed a circuit that shows chaos. So I have constructed this circuit. I have it somewhere here. Where is it? Do I have it here? No. This is okay. So, well, I suppose that you don't know this, but one way to analyze electronic circuits, this is like, you know, you tear apart a radio at home and you will get something like this, plus the batteries.
Should we turn on the light?
Yes, please. Yeah, I'm finishing. Okay, so the way to study this is with something called an oscilloscope. Probably you have seen something when you take your car to repair this day. The guy do not open the hood and look and say, switch on the engine. It just plugs something into your car and an oscilloscope or whatever tell it what is wrong with it. Obviously they charge you accordingly, which is what happened. But okay, I could have brought it here and plug it into my circuit, which is the Chua circuit. The Chua circuit is this. It is essentially, these are capacitor, there are resistance, these are coils, etc. And this is something very important, which is a non-linear piece of electronic thing, which is called the Chua diode. Essentially, diodes behave non-linear. Okay, but then you could put the oscilloscope here and see the chaos. So what I'm going to do, something more simple. I'm going to put it a loudspeaker and we will hear chaos. It's not the same thing, but you know, for the price that we have all paid, that's enough. Now, some of the time I can do it with the oscilloscope if you are interested. Well, you hear something? But you know, the key thing is that I'm going to change the resistance of my circuit with this screwdriver that I have here. You know, it's a knife. Okay, I have a resistance here which is variable. I change it. So here is regular. There is only one pitch. There is only one frequency. E, whatever it is, but it's only one. So if I move it, the resistance a little bit, it changes. Okay, I should have done it the other way around. Okay, it changes. At some point it bifurcates. It gets 2. Well, we don't hear it, but at some point you get 2, 4, 8, and at some point you get so many frequencies that it's chaotic. And you can see this is noise, right? Well, you can see it in the oscilloscope pretty well, but you know, some of the time. Next time you can see it. I promise that I will show it to you. So you will get things like that, right? And I don't know, I can stop here or I can do you a oscillatory chemical reaction. 10 more minutes? Yes. Okay. Then, this is the last thing that I prepared. Okay, what is this? This is something to make a reaction. I'm going to have a beaker. And I have something that we call the flea, which spins. Let's see if I find it with the coin. I put it here so that I do not lose it. Okay, it's here. So there is essentially there is a magnet with a plastic. So if I put it here, you see it goes around. Okay, now I have my recipe, like every witch has, which is, says 150 millimeters of water. Water, I mean, here we have water, 150. Now comes the dangerous part, which is sulfuric acid, 96%. So this is, you have seen this. When somebody, usually in an Arab country, unfortunately, throw it to the face of a woman for ridiculous reasons, you know, the woman gets
Burned.
scars. So this is, they do it with this. So it is 15. So.
Mm.
Well, you see that, well, you are not here, but I mean, you see that there is very, it heats, because, I mean, the sulfuric acid likes the water very much. Let's say. Okay. So, now I put 1.8 grams of malonic acid. What? Malonic. If you care about it. Malonic acid, which is CH2COOH2. You ask for it. So, where do I have the malonic acid? Where do I have it?
Not in my bag.
I leave it in the car. I leave it in the car. Oh my God. I cannot do it. I leave it in the car.
Okay.
I'm sorry. Okay,
No
but
problem.
I will show you something will happen. Ah, I hate myself.
No,
I
no,
thought I
don't
had
do
brought
it.
everything. How do I? Well, you know, the thing is, I threw the malonic acid. I threw something which is bromate, potassium, and magnesium sulfate. So it is. It gets something like it is like pink, very pale pink, and you wait for a while, you change color, and it is because there is a reaction. Okay, there is nothing. I mean, you can do reactions, everywhere. I mean, if you have acid in your stomach and you feel pain, you take antacid, and you know there is a reaction that neutralizes your acid in the stomach. But what happens with a reaction is that when you leave a chalk or whatever to leave, so the gravitational field bring it to a point where there are less energy. So there is something called free chemical energy. And the reaction goes from high chemical energy to low, but they stop there. But this reaction is just going back and forth, back and forth, back and forth. And the thing is that this guy, Belousov, was the first to observe this reaction working in the biophysics laboratory of the Ministry of Health. And nobody believed it. Say, this is wrong. Nobody published the paper for a long time, until his graduate student, Sabotinsky, followed that research, had a tremendous hard time getting his PhD thesis accepted, but eventually people realized that those reactions were possible, because what I say, that one reaction happened from reactant to product and stop, happened if everything is in equilibrium. Okay, this is a very fundamental law of thermodynamics. Systems go through equilibrium. It's like in a battery. In a battery, the electron goes from high voltage to low voltage until all electron has done the trick. And then the battery is not good anymore. But this reaction, because you see that I'm moving the beaker, it is in a non-equilibrium state. And then that reaction can happen. It took a long time to people to realize, and even to 1970s to realize. And then, well, the problem is that these reactions are pretty complicated. There are many steps. Many things are happening in the beaker. And what you see is if you measure the concentration of one of the reactants, you see that they oscillate. And these oscillations are chaotic. Do you remember? Do you see how they are very similar to the first simulation I showed you with the driven pendulum?
Yeah.
Well, this is the thing. And that is all. With you know, there is a chain, usually a Chinese guy, which is like moving dishes and moving, and you know, when you have two dishes is okay, 3 is okay, 4 is okay, but you know, at the end, there are so many that one. Get crazy. So this is what has happened to me. So malonic acid, bromato potásico, and sulfato de manganeso, start smelling.
Oh, yes.
Well, I have not wait.
Are they safe over there?
Well, you
Oh,
see
yeah.
that it's pink, right?
Yeah.
If everything goes accordingly to the script, it should get no color in some time. You see?
Oh, yeah.
Voila. Pink again, no color, pink again, no color, pink again. And you know, it can be here for, I mean, like 1 hour doing like that. And if we will measure, it will be chaotic. Next time we can do it.
Okay.
Next time we can make a measure. Well, that is all now.